In this video, I want to start my Statistical Mechanics playlist with a thought experiment, which we call the unbiased coin. So what is the unbiased coin? Let's write it. The unbiased coin. So what is it? Well, an unbiased coin, as the name suggests, is a unbiased coin. Because in real life, if you were to flip a coin, it will not exactly be 50-50. There's gonna be some shift in the probability of heads or tails. Depends on maybe the angle that you flip a coin, or depends on the air pressure within the room that you're in flipping the coin. So these little micro thingies can really affect the probability, but at a very small scale, of course. So in the case of an unbiased coin, it is just 50% heads, 50% tail, with no bias, no other factor introduced. So let's consider the case with one coin. So assume we have one coin, which is unbiased coin. What are the possible outcomes? Well, the possible outcome is one head, one tail, right? These two are the only two possible outcomes, because if you flip the coins, it's either heads or tail. So in this case, the degree of freedom for one unbiased coin is going to be 1, because only one independent variable is required to describe its configuration. In this case, to describe the configuration of our coin, you only need one variable, right? And that variable could be either heads or tails. So we call the degree of freedom for one coin to be 1. And now we can look at a second scenario, which is when we have two coins. So the case with two coins. So what are the possible outcomes for two coins? Let me draw a line to distinct our one coin and two coin. But what are the possible outcomes? Well, it's either head, so two heads, or tail, so both tails, or head first, tail second, or tail first, head second, right? So these four are the only possible outcomes. And here I'm going to define something called a microstate. By the way, can you tell me what is the degree of freedom for our two coin scenario? So DOF is just going to be 2, right? Because each independent result from these, you can look at it. So what are the independent variable in here? Well, it's the first coin and the second coin, right? So the degree of freedom of independent variable in this case is 2. So the degree of freedom for a two unbiased coin is going to be 2. So I'm going to continue what I was talking about, which is defining something so-called microstate, which is extremely important in statistical mechanics. So a microstate is a state in which all the degree of freedom are determined. So in this case, our microstate for our two unbiased coin will be each one of these, right? It's head, tail, head, tail. Tail heads are all microstate of our system, because for each one of them, the degree of freedom are already determined. Because for heads, you have two variables, and in this case, they're both determined to be h. And for tails, they're both determined to be tails. For head tails, they're one to determine, first one being determined as h, heads, second one being determined as tails. So microstate is the state in which the allowed degrees of freedom are already determined. So another example would be something like a gas molecules in a box. So imagine you have a box, and there's only 3 gas molecules in there, so which we call 1, 2, and 3. So the microstate in this case, what is it going to correspond? This is going to correspond to the specific exact position XYZ of the microstate and the velocity for each of the molecule. I was talking about the position of the molecule, not the microstate. So in this case, the microstate would be, let's say, x1, y1, z1. So the position for molecule 1 in terms of x, y, z with velocity v1, v2, v3, and the second one be x2, y2, z2, v2, and you just continue that list as you go. So the microstate is a state in which all the degree of freedom are determined. Then another important concept, which we call the macrostate. So the macrostate is a combination of multiple microstates. So in this case of two unbiased coins, a macrostate, for example, could be exactly one coins that show H. So let's say our macrostate is exactly one coin shows H. This is our macrostate here. And then how many out of all four only has one H? Exactly show one H. Well, it's gonna be head, tail, and tail, head, right? So there's two. So contains two microstate, or at least one coin has H. So what is this? Well, we have head, 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 tail, and tail, head. So contains three microstate. So you can see macrostate is like a more general and a combination of microstates. And in cases of like gases, it would imply something like the pressure or the volume, temperature. These are all actually macrostates, right? Because it does not consider the niche, the individual particles of velocity and position. Like it is more like a combination of it contains multiple microstates. That is a more better definition. So now we move on to three coins. So for 3 coins, what are possible outcomes? 3 unbiased coins. So what are the possible outcome here? Well, it's gonna be head, 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 tail, 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 head, 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 tail, head, blah, 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 and continue. And the degree of freedom in this case is going to follow the logic of what we have before. When we have 3 independent variables, the degree of freedom is going to be 3. So let me ask you, what is the total number of macrostate that we have here? And each one of these are the macrostate, right? Like for each degree of freedom is already determined, like we defined above. So how many macrostates do we have here? Well, there's a formula that you can use, which is microstate. I think I just said macrostate, but forget about that. I've often mixed up both these two. Sometimes when I say them. So for microstates, there is a formula which can help us calculate the total number of microstates there is within the system, which is the possible values per DOF to the power of DOF. So in this case, for each degree of freedom, for each individual variable here, this is individual, this is individual, for each variables here, what is the possible value for each coin? Well, it's 2, right? Because you either get heads or tail. So that's the possible value per degree of freedom or per variable. And the variable in this case is 1 coin. The per variable, per degree of freedom here is the 1 coin. So it's going to be 2 and our degree of freedom is going to be 3. So there's a total of 8 microstates here. If you don't believe me, you can try to write them all down. It's not that difficult. And so there are a total of 8 microstates here. How about macrostates? What if we want to calculate macrostate? So example here I will give is, let's say, same one as above that we did in the 2 coins. So how many microstates shows exactly 1H? So exactly 1 coin show H. So how will we calculate this? We're going to use a formula which I'm going to write down and explain in just a second. So CNK is equal to n factorial k factorial n minus k factorial. In case you don't remember what factorial means, like say n factorial is n times n minus 1 times n minus 2. So for maybe 5 factorial will be 5 times 5 minus 1, 4 times 5 minus 2, 3 times 5 minus 3, 2 times 5 minus 4, 1. So this is the factorial, just a quick reminder. So how does, what is this formula here? What does this tell us? This formula give us, I'm going to write this down, it's very important. So how many ways can you get k heads from n coins? So n here represents how many coins we have in total. In this case, 3, right? We're flipping 3 unbiased coins, so that's n. And then our condition here says I want exactly 1 coin shows H. So our k here is going to be 1 because we can choose our k value, right? We can choose it by defining how many ways you can get k heads. So in this case, we're looking for the way, the number of microstate you can get 1 head, right? So 1 is going to be our k value because our condition is exactly 1 coin show H. So if we plug that in, so our n is going to be 3 coins, and we want to look for exactly 1 head. So this is going to give us 3 factorial over k factorial, so 1 factorial, which is 1, n minus k, so 3 minus 1 factorial, or is 3 factorial over 2 factorial times 1 factorial, which is 1. So the above is going to be 3 times 2 times 1, bottom is going to be 2 times 1. So it's going to be 6 over 2. It's going to be 3. So there are exactly 3 microstates out of all the 8 microstates we have here that have exactly 1 coin shows H. And if you have written this down, you can see down right by counting it yourself. So this formula gives us numbers of ways we can get k heads from n coin. Like you can put in the value 2 here to experiment yourself, like number of ways you can get 2 heads from the 3 coins, right? You can experiment with the formula if you want. And the next formula I want to introduce before wrapping this video up, which is the probability for a given microstate to occur. So probability for a given microstate to occur. So I didn't talk about probability part, but if we go back to our 2 unbiased coin, let me ask you, what is the probability of getting heads and heads? Like, what's the probability for each one of the microstate here? Well, it's 1 over 4, right? Because let's say you flip the first coin, what's the chance you get heads? 1 over 2. You flip it again, what's the chance to get heads? 1 over 2. Right, so 1 over 2 times 1 over 2 is going to be 1 over 4. So this gives you the probability of getting this microstate HH. And then this same logic applies to all of these, right? So they all have 1 over 4 probability of that happening if you were to flip it 2 times. You can grab 2 coins in your hand right now if you want. And if you flip them, you flip one of them, you flip the other one. And if they're both heads, the probability of that happening is 1 over 4. So a general formula we can use here is probability Kn is equal to number of microstate over total number of microstate. So in this case, if for our 2 coins, as you can see, for each one, our total number of microstates, we have 4 of them here, so 4 at the bottom. And then if we're just talking about tails and heads, it's going to be 1 at the top because you're choosing 1, right? But you could also ask, okay, what is the probability of obtaining heads or tail? So now you're choosing 2. So you have, well, the total number of microstates doesn't change at the bottom, so it's going to be 4. But you're gonna have number of microstates you want to choose at the top. So in this case, it's going to be 2, right? So the probability of you rolling either heads or tails is going to be 1 over 2. So you flip it 4 times, chance that happen. You flip it one, you flip both coins. The chance of you getting either heads or tails is going to be 1 over 2. So that's why this formula makes sense. So the number of microstates that we see in the previous formula that I have provided, this give us the number of total microstates. No, total number of microstates is this formula, which is possible values per degree of freedom to the power of degree of freedom. So in this case, so 2 to the power of n for our unbiased coin, right? Because you always get, because 2 is also always constant, right? Because no matter how many coins you get, you can only flip heads or tail. So the possible value per degree of freedom never changes because you can only get heads or tail. But the degree of freedom could change, depends on how many coins you have. So the total number of microstates is going to be 2 to the power of n. And the number of microstates here is going to be with this formula, right? Because this formula gives us how many ways you can get k heads from n coin, right? So this is the choosing part, which is similar to what we talk about here. This is the choosing part rather than the total part. So if we plug in this formula, it's going to give us n factorial over k factorial n minus k factorial. So this formula gives us the probability of for a given microstate to occur. And you can play around with this formula. Like for example, we were just talking about exactly 1 coin shows h, right? And then we have 3 on the top, and then the total number of k's, total number of microstates in this case will be 8 on the bottom, right? Because 2 to the power of 3, or degree of freedom for 3 coins 3. So the probability of you getting exactly 1 coin show h is 3 over 8. Because there are exactly 3 microstates in which all of them has exactly 1 coin source h, and that over the total number of microstates, which is going to be 8 in this case, is going to give you the probability of what you have chosen to occur. And that is a brief introduction to the unbiased coin. And in my next video, I'm going to talk about binomial distribution. And thank you for listening.